In this lecture, we will discuss what properties a continuous time periodic signal must satisfy in order for it to have a Fourier series representation. And then we will also discuss some important properties of the Fourier series itself. But before we move into that, let us quickly recall what we did in the previous lecture. And we said that a periodic signal, a continuous time periodic signal x of t, can be represented in terms of the Fourier series as this infinite sum, x of t equals this infinite summation of ak e power jk omega naught t, and this we call as the exponential Fourier series. And the terms ak, okay, the parameter ak is called, these are called as the Fourier series coefficients, and those can be computed by this integral. Okay, and we also saw previously how to convert this exponential form of the Fourier series to the sine cosine form of the Fourier series. And when you go to the sine cosine form of the Fourier series, we have this Fourier series coefficient small a sub 0, which represents the DC component of the signal x of t. And then we have these new terms, capital AK and capital BK, which can be obtained from the small ak terms. Okay, so capital AK is nothing but small ak plus small a minus k, and this capital BK term is j times small ak minus small a subscript minus k. Again, this is something which we have seen in the previous lecture. What we want to see is, first of all today, what is the condition that the signal x of t must satisfy in order for it to be accurately represented by this series expansion. And these are called as the Dirichlet conditions. So the Dirichlet conditions are the conditions that a signal x of t, periodic signal x of t, must satisfy in order to guarantee that its Fourier series representation is exactly equal to the actual signal x of t. And the first Dirichlet condition is that the signal x of t must be absolutely integrable over any period of the signal. So if we integrate the signal over any period, the magnitude, the absolutely integrable, that means the absolute value of x of t is integrated over any period, and that should be a finite number. And this is one of the conditions that must be satisfied for a series to have a Fourier, for a signal x of t to have a Fourier series representation. Most of the signals that of interest that we come across will satisfy this condition, but just to illustrate an example of a signal which is periodic but does not satisfy this condition is this x of t equals 1 by t. And because this time t is in the denominator, so when t is approaching 0, this 1 by t is approaching infinity. So when the time t is 0, the 1 by t is approaching infinity. So that means for a signal to be absolutely integrable, what it means is that in any period of the signal, there should not be any time instant at which the amplitude of the signal or the magnitude of the signal is infinite. So this particular signal, which is x of t equals 1 by t, and when t equal to 0, its magnitude is 1 by 0 is infinity. So we say that this is not absolutely integrable. That means if you integrate over one period, the answer will not be finite, and therefore even though the signal is periodic, it is having a period of 1, it is repeating, it is having one cycle from 0 to 1, and then from 1 to 2 it is having its second cycle, and so on. So it is having a period t equal to 1, but it is not absolutely integrable. That means in any period, if we integrate this, we get a value that is not finite. That means it is not less than infinity. So therefore, this particular signal does not satisfy the first of the Dirichlet conditions, and therefore we cannot have a Fourier series representation for this particular signal. So the first condition a signal must satisfy in order to be represented in terms of the Fourier series is that the signal should be absolutely integrable over any period. The second condition that a signal must satisfy is that in any given period, it should have a finite number of maxima and minima. So if we look at this signal, this is a signal which satisfies both the conditions, condition 1 and condition 2. And this is an example that we discussed in the previous lecture as well. So we synthesize this using the Fourier series representation. So therefore, it clearly has a Fourier series. And if you look at this particular signal in one particular period, in one period, the number of maxima and minima is finite. So we have one maxima here and one minima here, and there's another minima here, and we come back here. It completes one cycle, that's one period, and we have another maxima here. So in one period, it is having a finite number of maxima and minima. So this particular signal satisfies this second Dirichlet condition as well. Whereas the plot shown at the bottom here is an example of a signal which satisfies the first condition. That means it is absolutely integrable, but it has infinite number of maxima and minima. So this signal is x of t equals sine 2 pi by t, representing this in terms of sine 2 pi ft. So it's like sine 2 pi t by t square. So that means the f corresponds to 1 by t square. The frequency of this sine wave is 1 by t square. And that means when t is approaching 0, when the time t is approaching 0, the frequency value is 1 by 0, which is infinity. That means if the frequency is infinity, as we move towards t equal to 0, it has infinite cycles in 1 second. That's what the frequency means. So infinite cycles means it is oscillating at an infinite rate. That means it was having infinite maxima and minima. So these maxima, the highest peak and the lowest peak here, the highest peak here and the lowest peak, the highest peak, right? So within one time period of the signal, there are infinite maximas and minimas. So therefore, this signal violates the second Dirichlet condition. Okay, even though it satisfies the first condition, that it is absolutely integrable within one period. So if we integrate the signal over one period, it will give us a finite value, because the positive and negative cycles will cancel out, resulting in a finite value for the integral over one period. But it has infinite number of maxima and minima in each period. So this is an example of a signal that does not satisfy the Dirichlet condition number 2, which is that the signal should have a finite number of maxima and minima during any period of the signal. The third condition that a signal must satisfy in order for its Fourier series to exist is that the signal should have a finite number of discontinuities in a finite interval of time. Now, first thing here is, the first definition that you need to understand here is the meaning of a discontinuity. Okay, a discontinuity is in a signal is basically a part of the signal where it has an abrupt, sharp change. So in this particular case, all these vertical lines, okay, the vertical line components of this waveform denote discontinuity. So we have this vertical line, that's a discontinuity, and that is a vertical line, that's a discontinuity. So at this time instant, the signal is having a sharp or abrupt change from the positive highest peak value to the negative peak value, right? So there's an abrupt change in the signal that we call as a discontinuity in the signal. And what this third Dirichlet condition tells us is that over a finite duration of time, the number of discontinuities should also be finite. So if this condition is satisfied, then even though the signal is having discontinuities, we would be able to represent it in terms of the Fourier series expansion. So this is a rectangular waveform or a pulse waveform where we have a finite number of discontinuities in a finite interval of time. So the interval of time is finite, and within that finite interval of time we have a finite number of discontinuities. So therefore this signal can be represented in terms of its Fourier series. Whereas this signal at the bottom here is an example of a signal that is having infinite number of discontinuities. So you see here, that's a discontinuity, so that's a vertical line, and that's a vertical line, and that's a vertical line. So it is divided into sections where each section is half the width and height of the previous section. So the second section is having a width which is half of the first section, and a height which is also half of the previous section, and this continues. So basically what happens is each time the width and the height is becoming half of the previous value. So there are an infinite number of discontinuities within one period. So one period is 8 time units. So within one period there are infinite such discontinuities. There's an abrupt change here. This vertical line is a discontinuity. This vertical line here is a discontinuity. Again here is a discontinuity. Again here it's a discontinuity. It becomes smaller and smaller and smaller, but it doesn't become zero. So there are an infinite number of discontinuities within each period. So this particular waveform does not satisfy the Dirichlet condition number 3, and therefore it does not have a Fourier series representation. So there are 3 conditions that a signal must satisfy for it to have a Fourier series representation. The first condition is that it must be absolutely integrable over any period. The second condition is that in any period it should have a finite number of maxima and minima. And the third condition is that in a finite interval of time it should have a finite number of discontinuities. So the number of discontinuities should be finite, and each of the discontinuities should also be finite. That means this vertical line should have a height that is also finite. If this vertical line is having an infinite height, then even though if we may have a finite number of discontinuities in a given time, if any of these lines is having an infinite height, then the discontinuity is not finite. So we should have a finite number of discontinuities, and each of the discontinuities should also be finite. That guarantees that the signal will have a Fourier series representation. So if a signal is satisfying all the 3 Dirichlet conditions, then it is guaranteed that the signal x of t is equal to its Fourier series representation. However, the Fourier series representation at certain instance of time will not be equal to the original signal x of t. What are those values of time at which it is not equal to the original signal x of t? That instant of time is basically where the signal is having the discontinuity. So where we have this vertical transition, abrupt transition, at this instant of time, that is at 0.5 seconds, I've plotted this waveform where the time axis is in milliseconds. So 500 corresponds to 0.5 second. So at 0.5 second there is a discontinuity here. So at this point of discontinuity, if we have the Fourier series representation, then the value of the Fourier series representation at that particular time would be equal to the average value of the value that is on the positive on either side of the discontinuity, that is. So that's the discontinuity. On either side of the discontinuity, the value is plus 0.8 and minus 0.8. So if we take the average of this value at this instant of time, the average is 0.8 and of plus 0.8 and minus 0.8 is basically 0. So at t equal to 0.5 seconds, that is 500 milliseconds, the value of x of t produced by the Fourier series would be equal to 0. And that's what we mean by the Fourier series representation value will converge to the average of the values on either side of the discontinuity. So at this discontinuity, there is on the top side the value is 0.8, and at the bottom side the value is minus 0.8. So at this time of discontinuity, the Fourier series representation of x of t will converge to the average of these two, which is the average of 0.8 and minus 0.8, which will be in this particular case 0. If we had another pulse whose value was, say, going from 0 to 1, then the average of 0 and 1 would be 0.5. So it will converge to 0.5 at the discontinuity. Similarly here, it will converge to 0.5. Right? In this case, we have plus 0.8 and minus 0.8, so the average value is 0, so it will converge to 0. Now, let us look in more detail what happens when we try to represent a periodic signal which has discontinuities like this square waveform in terms of the Fourier series. Now, this is something which we have seen also in the previous lecture, where we tried to synthesize the square waveform using sinusoidal, by adding sinusoidal waveforms, which is by summing up the Fourier series terms. So normally the Fourier series is represented using this infinite summation term, right? This is infinite summation term. But out of these infinite terms, if we add only a few selected terms, we get some close representation of the actual signal. So we see here that's our original signal x of t, and this is the synthesized signal, synthesized by adding just 3 harmonics of the Fourier series. Now we see that there are ripples in the synthesized waveform. So we see that there are ripples in the vicinity of the discontinuity. So the discontinuity is the point of time corresponding to this vertical segment of the waveform. So in the vicinity, in the neighborhood of the discontinuity, there are ripples. So the ripples, if you see here, if we add more and more harmonic components in the Fourier series, so that's 3 harmonics. Now I've added 5 harmonics here at the bottom here. It's the synthesized waveform with 5 harmonics, and here we have the synthesized waveform with 25 harmonics, and here we have the synthesized waveform with 250 harmonics. Now what we notice is that as we add more and more harmonics, that means as this n value, the number of harmonics tends to infinity, the synthesized waveform becomes closer and closer to the actual waveform x of t, the actual signal x of t. And we see clearly here, when we have 250, this is a much closer representation of this x of t as compared to xn of t when n is equal to 3. So that's the first observation we make. Then we see that in all these cases, in the synthesized waveforms, there are some ripples in the vicinity. In the vicinity means in the neighborhood of the discontinuity. So the discontinuity is this time instant at which we have these vertical segments of the waveform. In that neighborhood, we have some ripples here. In that neighborhood, we have ripples. Again, we have ripples here. Okay, and the second observation regarding this is that the peak amplitude of the ripple, okay, is the same irrespective of the value of n, whether we have n equal to 3, n equal to 5, 25, 250, 2500, or even infinity. This peak amplitude, the peak amplitude of this ripple, the peak amplitude of the ripple in all these cases is fixed, and that is equal to 9% of the total height of the discontinuity. And again, that's the analysis and proof done by the scientist called Gibbs, who proved this phenomena, and hence by his name, this phenomenon in the Fourier series representation where we have ripples, this is called as a Gibbs phenomenon. Okay, so First of all, Gibbs phenomenon states that when we are trying to represent the discontinuous signal in terms of the Fourier series, we will see ripples in the neighborhood of the discontinuity. The second observation is that the peak amplitude of the ripple will be fixed to 9% of the total height of the ripple, irrespective of the value of n. But what we do notice is that as we increase the value of n, even though the peak amplitude is the same, what we notice is that the ripples get compressed towards the discontinuity. So we see here the ripple is more in the middle, but as we increase n, the ripples are getting compressed to closer and closer to the discontinuity part itself, that is closer and closer to the vertical segment of the waveform, right? So as n increases, the ripples get compressed toward the discontinuity. And finally, the overshoot occurs near the discontinuity of the signal. Okay, now what we have seen previously is that at the discontinuity, the value of the synthesized signal will be the average value of the values that are on either side of the discontinuity. So here it's plus 0.8 here and minus 0.8 here. So at that moment of time, the value of the synthesized waveform x1 of t will be the average of this top value and the bottom value. Okay, now in this particular example, we have the height of the discontinuity as 1.6 because it's from 0 to 0.8 on the positive side and minus 0.8 on the negative side. So the total height here is 1.6, and when we add 9% of 1.6 to 0.8, that becomes something like 0.944. And that is exactly what we see here. The peak amplitude of each of these ripples here is between 0.8 and 1. The middle point is 0.9, and it is slightly more than 0.9. It's exactly 0.944. So you can calculate that. Okay, you can calculate 9% of 1.6 and add it to 0.8. You will find that it is equal to 0.944, and that is the peak amplitude that we see here. Okay, so basically these ripples that we see in the Fourier series, the representation of periodic but discontinuous signal, that is, this is a signal which has discontinuities. This is called as Gibbs phenomenon. Okay, and you need to understand what this and you need to be clear as to how to interpret the Gibbs phenomenon and the ripples that occur as a result of the Gibbs phenomenon. And just to illustrate that at the discontinuity, the value of the synthesized waveform is the average of the values on either side of the discontinuity. I've just shown an enlarged version of the synthesized waveform for n equal to 3. That is when you have only 3 components. We see now at the discontinuity point, okay, where we have the vertical edge. So at 0.5, the value of the synthesized waveform is halfway, the average of 0.8 and minus 0.8, which is 0. So that's the average value of the signal. So at 0.5, the average value is 0. Similarly, at 1, it is the average of minus 0.8 and plus 0.8, which is 0. At 1.5, it's also 0. So at each of the discontinuities, we have the value of the synthesized waveform xn of t to be equal to the average of this positive peak, that is the value on one side of the discontinuity and the value on the other side of the discontinuity, right? So that's the value we have here. So that's the discontinuity. So at the discontinuity, the values that you have on either side is plus 0.8 and minus 0.8. So the synthesized value would be the average of these two, which is plus 0.8 plus minus 0.8 divided by 2, which is 0. So we have it for all these particular points. So just to illustrate this, I've shown an enlarged version of the synthesized waveform with n equal to 3. So let us now move on to discuss some of the properties, some important properties of the Fourier series of continuous time signals. So we'll be looking at various interesting properties which can be used in solving problems, and also to understand what happens when we perform certain alterations to the signal. What is the effect on the Fourier series coefficients? Okay, but before we go into the properties, we need to first agree on the notation that we are going to follow. The notation is that if we represent a signal, a periodic signal, as x of t, and if we take the Fourier series of that signal x of t, we get the Fourier series coefficients which we denote as ak. So we will represent that process as such. So x of t, when taken the Fourier series, gives the Fourier series coefficients ak. So this is the standard notation that we are going to follow in the entire discussion that follows in this lecture. The first property that we are going to see is what we call as the linearity property, and that is something that we have already seen when we talked about linear time invariant systems. So the same principle applies. So in this case, consider that we have a signal x of t whose Fourier series gives its Fourier series coefficients, which we denote as a subscript k. Consider that there is another signal y of t whose Fourier series gives us its Fourier series coefficients, which we denote as bk. Now, if we construct a third signal z of t as a linear combination of x of t and y of t, that means x of t multiplied or scaled with some constant plus y of t scaled with another constant, capital B, then we can find the Fourier series coefficients of z of t. Okay, if we take z of t and take its Fourier series, we will get its Fourier series coefficients, which we can call ck. But these Fourier series coefficients will themselves be linear combinations of the original signal's Fourier series coefficients. So since z of t is a linear combination of x of t and y of t, its Fourier series coefficients ck are also a linear combination of ak and bk. So it is the ak is scaled by the same factor, capital A, that is scaling x of t, and bk is scaled by the same factor, capital B, that is scaling y of t. So the Fourier series coefficients ck of z of t, which is a linear combination of x of t and y of t, are a linear combination of the corresponding Fourier series coefficients of x of t and y of t. Okay, so that is what we call as the linearity property of the Fourier series. Next, we will see the second property of Fourier series, which is called as time shifting. So again, consider a signal x of t, which has the Fourier series coefficients ak. Now, if we shift the signal by some amount t naught, what happens to the Fourier series coefficients? The Fourier series coefficients will get multiplied with the complex exponential given by e power j k omega naught t naught. So if we shift it by t naught, it is multiplied by e power minus j k omega naught t naught. If this t naught is phi, it will be ak e power, each of these ak's will get multiplied with e power minus j k omega naught into phi. If this is 10, this t naught will be 10. If this is minus 10, this t naught will be minus 10, and so on. So a shift in the time domain corresponds to a multiplication in the frequency domain with the complex exponential signal. So each of the Fourier series coefficients of the original signal x of t are getting multiplied with this complex exponential as a result of shifting. So if we shift x of t by t naught, then the corresponding Fourier series coefficients get multiplied with the complex exponential. That means we say that a shift in the time domain corresponds to multiplication with the complex exponential in the frequency domain. Now, when this change is happening, okay, between the original signal and the shifted version of the signal, the only change is that the Fourier series coefficients get multiplied with this complex exponential. And what you will notice is that the magnitude of both these Fourier series coefficients are the same. So the magnitude of AK and the magnitude of AK e power minus j k omega naught t naught is the same. And you can prove this in a very simple way by using the Euler's formula for e power minus j k omega naught t, which is cosine k omega naught t naught minus sine k omega naught t naught. So substitute and to find the magnitude, basic concept of complex numbers, and you'll be able to prove that the magnitude of the original signal, the magnitude of the Fourier series coefficients of the original signal x of t and its shifted version are going to be the same. Okay, so the magnitudes of the Fourier series coefficients are not altered as a result of the time shift. So I'll leave that as an exercise for you to make that proof, but it is fairly straightforward. It requires just to substitute the Euler's formula here and use basic concepts of finding the magnitude of a complex number. So I'll leave that for you as an exercise. The next property of Fourier series that we are going to talk about is called as frequency shifting, which is like the converse of the time shifting. So in time shifting, when we shift in the time domain, it gets multiplied with a complex exponential in the frequency domain. Similarly, when we multiply a signal with a complex exponential in the time domain, its Fourier series coefficients get shifted in the frequency domain. Okay, so basically if we have a signal x of t with Fourier series coefficients ak, then if that x of t is multiplied with a complex exponential in the frequency domain, what happens to the Fourier series coefficients? The Fourier series coefficients get shifted by the same factor m, that is representing the harmonic component of this e power j omega naught t. So what it basically means is that multiplication with a complex exponential in the time domain corresponds to a shift in the frequency domain. The Fourier series coefficients get shifted by the same factor. So this is also called as frequency translation or the modulation property of Fourier series. And we will also see that the same property applies for Fourier transforms for aperiodic signals as well. Okay, and this is a concept that we'll use in future courses in higher levels, where you study communication systems and in which you will study about modulation and so on. So this is an important property that will be handy if you understand, if you have a clear understanding. So it will be useful in future courses when you talk about communication systems and analog communications and so on, where you will study modulation of signals for communication purposes. So this is called as a frequency shifting property. That means multiplying a signal with a complex exponential in the time domain produces a shift in the frequency domain. So it is like the converse or dual of the time shift property. Shift in the time domain is equivalent to multiplying with a complex exponential in the frequency domain. Correspondingly, multiplying in the time domain with a complex exponential corresponds to a shift in the frequency domain. The next property that we're going to see is the time reversal property. And what this property says is that if we have a signal x of t with Fourier series coefficients given as ak, then the Fourier series coefficients of the time reverse version of x of t, which is x of minus t, is simply equal to a subscript minus k. So you just reverse the k terms here in the Fourier series coefficients, and that will give you the Fourier series coefficients for the time reverse version of the signal. So if x of t is having Fourier series coefficients ak, then x of minus t will have Fourier series coefficients a minus k. Now this gives us some interesting properties, observations, when we consider that the signal x of t is an even signal. So if x of t is an even signal, it means that x of minus t is equal to x of t. That's the meaning of an even signal, right? And so if our signal x of t is even, then x of minus t is equal to x of t. So that implies, so therefore it implies that a minus k is equal to ak. That means if the signal is even, then the Fourier series coefficients are also even. So that means a minus k is equal to ak. That is, the Fourier series coefficients are also even. Now, if the signal x of t is odd, that means x of minus t is equal to minus of x of t. In this case, the Fourier series coefficients a minus k will be equal to minus of ak, right? Because x of minus t is minus of x of t. So that means a minus k will be minus of ak. So the corresponding Fourier series coefficients are also odd. So we can write that as, that is, the Fourier series coefficients are also odd. So if the signal x of t is even, then its Fourier series coefficients are also even. And if the signal x of t is odd, then the Fourier series coefficients are also odd. Next, we will see the property of time scaling of the Fourier series. That is, if you have a signal x of t with Fourier series coefficients ak, what is the Fourier series coefficients of x of alpha t? So that is the time scaling operator. Again, that is some of the transformations of the independent variable that we have seen right in the beginning of the course. So that's scaling the time axis, which is scaling the independent axis. So x of alpha t has Fourier series coefficients which are the same as the Fourier series coefficients of the original signal. So by scaling the time axis, okay, we see that the Fourier series coefficients ak themselves do not get changed. However, the Fourier series itself changes. Okay, the Fourier series of both these signals is not the same, even though the Fourier series coefficients are the same. The reason is because while the signal x of t has the Fourier series representation given by this infinite series, which is aka e power j k omega naught t, x of alpha t has this Fourier series representation given as ak summation ak e power j k alpha times omega naught t. So it is k omega naught, but here it is k times alpha omega naught t. The reason is because x of t, if it is having a period t, then x of alpha t, scaling the time axis, makes the scales the period as well. So if x of t is periodic with period capital T, then x of alpha t is periodic with period t by alpha. So the harmonic components, okay, the fundamental harmonic component here is omega naught, and here it is going to be alpha times omega naught. So while the coefficients themselves do not change, the fundamental harmonic is different for x of t and x of alpha t. So the time scaling operation does not change or alter the Fourier series coefficients, but it changes the Fourier series itself, because those coefficients are now representing different harmonic components as compared to the original signal, which is not scaled. The next property is of multiplication. So what happens if we have two signals x of t and y of t in the time domain with corresponding Fourier series coefficients ak and bk? What would be the Fourier series coefficients of the product of these two signals? So if we multiply x of t and y of t and produce a new signal, if you can call this as z of t, which has Fourier series coefficients hk, then we find that these the Fourier series coefficients of the product of these two signals x of t and y of t is nothing but the convolution of the individual Fourier series coefficients, that is the convolution between the Fourier series coefficient of x of t and the Fourier series coefficient of y of t. So it is the convolution of ak and bk, which is, if you recall, the convolution operation is summation x of n, we can write x of k times h of n minus k, right, for k equal to minus infinity to infinity. So here it is written as like a l b of k minus l, right? So it's basically the convolution between ak and bk. So what we see here is that when we multiply two signals in the time domain, in the frequency domain, their corresponding Fourier series coefficients get convolved. So there is a convolution between the corresponding Fourier series coefficients of the two signals. So if x of t is having Fourier series coefficients of ak, y of t is having Fourier series coefficients given by bk, then the Fourier series coefficients of the product of these two signals is basically equal to the convolution of the these Fourier series coefficients of the individual corresponding signals. And again, this is an important property of the Fourier series that you should bear in mind, and it will come handy in a lot of courses in the future and in a lot of analysis that we do here. So basically, multiplication in the time domain is equivalent to convolution in the frequency domain, and the opposite is also true, and that is the next property that we are going to see. Just as multiplication in the time domain is equal to convolution in the frequency domain, convolution in the time domain will become multiplication in the frequency domain. So if we have two signals x of t and y of t with their respective Fourier series coefficients ak and bk, then if we produce a third signal, which is by performing the convolution between x of t and y of t, then the Fourier series of this convolution output would be the product of these individual Fourier series coefficients. So the convolution of x of t and y of t over a single period t will have a Fourier series given by the product of ak and bk times the time period t. So since we are taking the convolution over a single period, so the product of these Fourier series coefficients ak and bk also gets multiplied with this time period t. So multiplication in the time domain is convolution in the frequency domain. Similarly, convolution in the time domain is multiplication in the frequency domain. So these are important statements that you should remember, and they will come in handy in a lot of analysis that you'll see in this course, and also in quite a few courses that you will come across in your higher levels. The next property is what we call as the conjugation and the conjugate symmetry property of the Fourier series. So again, if we have a signal x of t with Fourier series coefficients ak, then what will be the Fourier series coefficients of the complex conjugate of x of t? So if x of t is a complex signal, if we take the conjugate, that means reverse the sign of the imaginary part. What will be the Fourier series coefficients of this complex conjugate signal of x of t? And it turns out that the Fourier series coefficients of the complex conjugate of x of t are nothing but the AK values, the original Fourier coefficients, conjugated and reversed in time. So the Fourier series coefficients of x star of t, x conjugate of t, is basically equal to a star minus k, which is nothing but what it says is that taking the conjugate of the periodic signal x of t has an effect of taking the conjugate of its Fourier series coefficients and reversing in time. So there is a conjugate effect here on the Fourier series coefficients. So AK becomes AK star, and also the k which is the minus sign. So there is a time reversal of the Fourier series coefficients as well. So that's a property of the Fourier series, wherein taking the complex conjugate of x of t produces the effect of making the Fourier series coefficients also to be complex conjugate of the original coefficients and also reversed in time. Okay, now if the signal x of t is a real signal, that means the imaginary part is 0, then the complex conjugate will be equal to the original signal itself. So when x of t is a real signal, then x star of t, the complex conjugate of x of t, is equal to the original signal x of t. In what that implies is that if this condition is true, that is when x of t is real, therefore x star of t equal to x of t, that means this AK and A minus K star have to be equal, because x star of t is equal to x of t. So that means when the signal x of t is a real signal, then the Fourier series coefficients AK and A minus K are complex conjugate of each other. So AK is A minus K star, or A minus K is A K star. So the Fourier series coefficients for negative k will be the complex conjugate corresponding to the positive k values for AK. Now, continuing further, if the signal x of t is real, we can deduce several more properties of the Fourier series coefficients. So I'm just writing down the mathematical statement that the Fourier series coefficients AK and A minus K are complex conjugate of each other, and from that we can derive or deduce some other properties of the Fourier series coefficients. So to illustrate that further, let's just say that AK is a complex number, okay, which is 2 plus j3. Then by this relationship, for x of t is real, A minus K is the complex conjugate of AK. So therefore, A minus K is the complex conjugate of AK. So that means we have to change the sign of the imaginary part. So A minus K is 2 minus J3. So looking at AK and A minus K here, we can say that the real part of AK and the real part of A minus K is the same. So it's 2 here and it's 2 here. So real part of AK and the real part of A minus K, they are both equal to 2 in this case, right? So in general, for real signal x of t, the real part of AK and the real part of A minus K are equal. Similarly, we notice that the imaginary part of AK and the imaginary part of A minus K have opposite signs. Here it is plus 3 and the imaginary part here is minus 3. So the imaginary part of AK is equal to the negative of the imaginary part of A minus K. And if we take the magnitude of AK, it is square root of A square plus B square, right? Which is square root of 2 square plus 3 square. So that's the magnitude of AK. And similarly, the magnitude of A minus K is the square root of 2 square plus minus 3 square, which is giving us the same value. And from that, we can deduce that the magnitude of AK is equal to the magnitude of A minus K when x of t is real. And finally, the phase of AK, which is tan inverse of B by A. When we have complex number A plus JB, then the phase is tan inverse of b by a, tan inverse of 3 by 2, and here the angle is going to be tan inverse of minus 3 by 2. So we see that the phase of AK is the negative of the phase of A minus K. So what that means is that the magnitude spectrum of a real signal has even symmetry, and the phase spectrum of a real signal has odd symmetry. Okay, and AK is equal to minus A minus K, the magnitude terms, that's even symmetry. And when AK, the phase of AK is the negative of the phase of A minus K, we say this is odd symmetry. It's like x of t equal to x of minus t and x of t equal to a minus of x of t, right? That's even and odd definitions which you are familiar with. So when x of t is a real signal, the magnitude spectrum has even symmetry and the phase spectrum has odd symmetry. We can extend this further for a signal which is not just real but also an even signal. So if we have a signal which is real as well as even, again we have seen what happens to the AK terms when the signal is even previously. So we'll combine both the properties. So when the signal x of t is real, then the Fourier series coefficients are complex conjugate of each other. AK and minus AK are complex conjugate of each other. And when the signal x of t is even signal, then A minus K is equal to AK. And if a signal is both real and an even signal, then both these conditions must be satisfied. That is, A minus K should be equal to AK star, as well as A minus K should be equal to AK. And that means this AK and AK star must be equal. So if AK and AK star is equal, that means the Fourier series coefficient AK and its complex conjugate is equal. That means AK is real valued. So if the signal x of t is real and even, then the Fourier series coefficients AK are also real and they are of course even by this property, because A minus K is AK, and since this A minus K is AK star and this A minus K is AK, it implies that this AK star is equal to AK, and that is possible only when the AKs are real valued. Okay, so for a signal x of t which is real and even, the Fourier series coefficients are also real and even. Similarly, if the signal x of t is real and odd, then it must satisfy the condition that AK star is equal to minus AK, right? Because for the real signal, this condition has to be satisfied, and for the odd signal, this condition has to be satisfied. So we see that A minus K is this and A minus K is this. So if the signal is both real and odd, then both these conditions must be satisfied. So that implies that AK star is equal to A minus K. Is equal to minus AK, right? Minus AK. So that can be true only when the Fourier series coefficients AK are purely imaginary. If you want both these conditions to be satisfied, that means the complex conjugate of AK is equal to the negative of AK, and for that to be true, AK must be purely imaginary and odd. Okay, that condition says it's odd, and for this condition to be satisfied, it also means that it is purely imaginary. That means in AK the real part is 0, so it only has the J term. So I've just taken an example here, that AK as J3, then A minus K, which is the complex conjugate of AK, which is going to be changing the sign of the imaginary part, so it will be minus J3. But A minus K should also be equal to minus of AK because it's odd. So if AK is J3, minus of AK is minus J3. So by choosing the value of AK, to be purely imaginary, both these conditions are satisfied, which is a minus k is equal to ak star, and a minus k is also equal to minus of ak, right? We see that this condition is satisfied. So what we see is that if the signal is a real and odd signal, then the Fourier series coefficients ak will be purely imaginary, and they will also be odd. And finally, we'll see this last but not the least, but a very important property of the Fourier series, which is called as the Parseval's relation. And basically, it gives us a relationship between the power of the signal, or it represents the power of the signal in terms of its Fourier series coefficients. So, if we have a periodic signal, and we can compute the average power by this formula, and that average power is nothing but it is also equal to the summation of the squared Fourier magnitude of the Fourier series coefficients. So the average power of the signal, which is x of t magnitude squared integrated over one time period, averaged over the time period, is equal to the summation over all the k's for the magnitude of ak square. So what this basically means is that if we know the Fourier series coefficients ak's for a particular signal, then we can compute the total average power of that signal by adding up these terms ak square, magnitude of ak square for all values of k. So that would give us the total average power of the signal. So the total average power in a periodic signal is equal to the sum of the average powers in all its harmonic components. So each ak is representing the magnitude of the kth harmonic component. So therefore ak, the magnitude of ak square, is representing the power in the kth harmonic component. So if we add up all the powers of the harmonic components, that should give us the total average power of the signal itself, because the signal is composed of those harmonic components. So if we add up the power in each of the harmonic components, that will give us the total average power of the signal x of t. Now we also want to show that each of these ak's or each of these ak square term represents the power in the harmonic component. So when k equal to 1, a1 square represents the power in the first harmonic. When k equal to 0, that represents the DC power. When k equal to 2, that is a2 square, that represents the second harmonic component, and so on. So we want to also show that each of the ak's is representing the power in the kth harmonic. So the kth harmonic component is ak e power jk omega naught t, because by the Fourier series, x of t is summation ak e power jk omega naught t. So for each value of k, we get the kth harmonic component. So the average power in the kth harmonic component is the integral of the squared magnitude of this term for that value of k, integrated over a time period t and average over that time period. So again, we simply apply Euler's rule here. So e power j k omega naught t is cosine k omega naught t plus j sine k omega naught t, and we're taking the squared magnitude of this. So we can write this cosine plus j sine k omega naught t magnitude as square root of the square of the real part plus the square of the imaginary part, which is square root of cosine square plus sine square. But cosine square x plus sine square x is equal to 1. So square root of 1 is 1, 1 square is 1. So that entire term is equal to 1. So that entire term here is equal to 1. So we end up with just this term, 1 by t integral over 1 period t magnitude ak square. So these ak's are the Fourier series coefficients, so we can take it out of the integral, and this basically becomes 1 by t, integration of dt over 1 period is t. So we get simply ak magnitude square. So that means that is representing the power in the kth harmonic component. So the average power in the kth harmonic component is ak square, and if we sum up all the powers in the harmonics, that gives us the total average power. So when we do the summation for all the k's for ak square, that gives us the total average power of the signal itself. So the signal is composed of the DC component, the first harmonic, the second harmonic, the third harmonic, and so on. So, and each of the harmonic components has a certain amount of power given by this magnitude square of ak square. And if we add up each of these individual harmonics powers, that will give us the total average power of the signal, which is what is depicted here. Okay, and this relationship is what we call as the Parseval's relationship for the Fourier series. So Parseval's relationship gives us the relationship between the power of the signal and its Fourier series coefficients. So basically we can compute the power of the signal by its frequency domain representation as well. Okay, so in this case for periodic signals, we take the Fourier series coefficients and add up the power in each of the harmonic components. That gives us the total average power. Okay, so we're going to stop here today, and okay, so we have covered in today's lecture the conditions that a periodic signal must satisfy in order for its Fourier series representation to exist. And we've seen some very important properties of the Fourier series itself, and you should be quite comfortable using these properties in solving problems, and you will also get some examples of using these properties to solve some problems in the tutorial session as well. Okay, so practice, that's what will make you comfortable dealing with these kind of problems in this course. And these are fundamental concepts, as I've said many times before, that will be useful in future courses for you. Okay, so we'll stop here for today, and we will be continuing with the next topic, which would be the Fourier series representation of discrete time periodic signals, which we will do in the next lecture.